Good afternoon, everyone. The mic is clearly on. That's great. Wonderful to see such a good turnout. It gives me simply enormous pleasure to introduce a friend of mine, Mike Bruton. I got to know Mike way back in 2009 when I was a foundation staff member and we were helping build this great university. And Mike was helping build it too. He was the researcher and the intellectual designer of our Museum of Science and Technology in Islam. And everything I know about that subject I learned from Mike and from our own museum. I think it's a really wonderful part of the university. Now, I only learned later, once I got to know Mike better, that although he's an expert in this field, the first half of his career was actually as a fish scientist, and a very famous one at that. And you can see he's just published volume 1 of his autobiography called When I Was a Fish. And there's a very strange looking fossil-like fish, coelacanth. And Mike is one of the world's experts in this. In fact, he's giving a talk to the Red Sea Centre tomorrow. So from the first half of his career as a fish scientist, he moved into science museums and public education. And that's how he came to be here. I know Mike doesn't want me to go on, but just very quickly, I'll mention a few of a very long list of awards. He's Emeritus Professor at the University of Cape Town. He has an honorary doctorate from Rhodes University, Lifetime Achievement Award, National Science and Technology Forum, South Africa, and extraordinarily from the government of France, Chevalier dans l'Ordre de Palme Académique. He's published 150 peer-reviewed papers and authored or co-authored 25 books on a variety of subjects. So that's quite enough from me. I would like now to introduce Professor Mike Bruton.
Thank you, Nigel. I think it was very much one of the goals of King Abdullah when he established this university to emphasize the universality of science. And I think in a small way we've demonstrated that now. Having a New Zealander introduce a South African to talk about Islamic science to an international audience in Saudi Arabia. Thank you very much for this opportunity. It's a great honor and privilege to be back. I'd also like to thank Marie-Laurie and her team for all the arrangements, and also greet my good friend Farouk Al-Janahi, with whom we had many adventures in establishing the museum. So the title is Quest for Perfection, Contributions of Muslim Scientists to the Golden Age of Islam. I haven't used the word pioneer, though that's our theme, because I believe that the scientists and technologists I will be mentioning were not only pioneers, but were masters in their field. They were the leading scientists and technologists of the day, many of them centuries ahead of their time. I'd also like to emphasize that I'm giving this talk from the perspective of a museum designer and an informal science educator, rather than an historian. It's basically divided into two parts, giving examples of some Islamic contributions, and then a discussion on why did science and technology flourish under Islam during that age. And obviously, in the short time available, I can only touch on a few topics. A golden age of Islam is defined in various ways. I'm using the 8th to the 13th century, although some discoveries and inventions after that are mentioned. And my hypothesis is basically that it laid the foundation for the Renaissance and the Industrial Revolution. Typical Western sort of concept of what happened during the Middle Ages is reflected in this quote from a British science author. After the Greek era ended, people turned back to myths, magic, and religion. For more than 1,000 years, superstition ruled the world, apart from a few glimmerings of scientific progress. But he does concede that knowledge of ancient Greeks was preserved by the Arabs. Now, that is a very ill-informed statement. Another typical example is what happened to the 1,300 years between the end of Greek civilization and the beginning of the Renaissance in Europe. Was it a scientific desert? And there we see a Renaissance painting of Greek scientists and then scientists much later missing out the Islamic Golden Age. In fact, Islamic scholars did far more than translate the work of the ancients, although that was an extremely important task that they did. As many of the great Greek authors, their works in the original Greek don't exist anymore. They only exist in the Arabic translations and the translations from that into Latin and English. They covered many different fields, and I will touch on some of them. I can first deal with architecture and design. Because artists, designers, sculptors were prohibited from depicting the human form or animal form, they developed a new form of art called the arabesque, which consisted of geometric patterns as well as plant forms in repetitive patterns. And quite often, it had a sort of dual unity in that individual units could stand by themselves, but they were also intricately linked to everything around them. And that really epitomizes the philosophy behind science during this golden era. There are many architectural contributions that have been made, and there we see the horseshoe arches at Alhambra in Granada, domes, rib vaulting, naves, porticos, the arabesque art form, mosques, minarets, maqanas, and mashrabias are just some examples. And there we can see different kinds of arches, the equilateral or pointed arch, the cinquefoil can also be trifoil, the ogee arch, and the double-centered one, overlapping arches and horseshoe arches. They became very popular and were continued in Western architecture. Once again, Alhambra, where the golden mean and the Fibonacci sequence were very much in the artist's mind when that magnificent palace was designed. The greatest architect and civil engineer in the Ottoman Empire was Mimar Sinan, and many of his buildings are some of the greatest buildings ever made. He constructed over 30 major buildings, as well as many civil engineering works, such as bridges and military installations. And his apprentices went on to design many other iconic buildings, including the Taj Mahal. Sinan was in contact with his great contemporaries in the West, Michelangelo and Leonardo da Vinci, who greatly admired his work. And there you can see one of his drawings, and you can see the geometry and the symmetry and the harmony that he is seeking. Domes were in existence pre-Islamic era, but they reached their magnificence and their huge size during the Golden Age. It was a time when new uses of arches, overlapping arches, star-shaped arches, made it possible to create enormous domes. Mashrabiyas, which are wooden verandas, covered verandas, also an architectural feature of that time. They provided a view of the outside while retaining privacy. And maqanas, which are kind of stalactites, three-dimensional niches, looking downwards from the arches and the domes, were another important architectural feature. The architects were also very practical. For instance, these budgo or wind catcher buildings, in which warm air was sucked down, cooled by the underground water, and then sucked up through the building through the Venturi effect. So predating by centuries the green architecture of today. And there we see an example of a 14th century windmill with its vertical vanes. In fact, windmills were seen in Islamic countries from the 8th century onwards. Because of the harsh climate in which many people lived, the towns and villages were also designed with sustainable living in mind and water-wise living. And we even have examples of medieval skyscrapers, such as these in Yemen. Let's move on to astronomy and mathematics, and I often link disciplines because the development of the one facilitated the development of the other. Al-Biruni was a classic polymath with expertise in a wide variety of fields. He was a mathematician who first described and predicted lunar eclipses with great accuracy. He wrote 96 books on geography and geodesy, estimated the circumference and radius of the Earth, and made many other contributions to mathematics, meteorology, and astronomy. Al-Kindi, regarded as one of the 12 great minds of history, a famous philosopher who worked in the first house of wisdom in Baghdad. Al-Kindi, one of his tasks was to supervise the translation of ancient works in Greek and Sanskrit into Arabic, and he did that for hundreds of volumes, and along the way read them and improved on the knowledge and understanding of those volumes. Al-Kindi was also one of the first people to write about music theory and to produce musical notation, and he was also a pioneer in the field of cryptography, the making and breaking of codes, and in one of his books explains how the frequency method worked. These are examples of some of their contributions to astronomy, and it's very significant that the leaders at the time, the caliphs and the kings, regarded having the best scholars, the best libraries, the best scientific and learning research institutes in their caliphate as a prestigious status symbol. So there was a great deal of support from the rulers and leaders for the development of modern observatories, the building of giant quadrants and sextants, which made astronomical measurements ever more accurate, building of celestial globes, which were spherical depictions of the heavens, armillary spheres, which were in two forms, tabletop forms, which were models of the solar system, and large ones which were used for observation. The astrolabe was originally designed, each astrolabe only for one location. Islamic scholars produced an universal astrolabe that could be used from any location. And using these different apparatus, they produced the most accurate astronomical tables ever created. They were aware that the Earth was round and measured its dimensions. They made many accurate predictions and calculations about the movements of the stars, eclipses, lunar eclipses, produced various solar system models, and along the way improved navigation. So there we can see an example, a scene where they're using these various tools that they had either improved or invented. And of course, astronomy and navigation was very important so that people could find their way while traveling for trade, also on pilgrimages, and especially because they were traveling across deserts with few landmarks and uncharted oceans. Here's an example of one of Al-Biruni's diagrams of lunar eclipses. And he not only drew them, but he provided mathematical formulae to explain them and predict them. In our various traveling exhibitions on Islamic contributions to science and technology, we've produced replicas of these inventions, and here's the universal astrolabe. And I might mention, Marie-Laurie has told me that this evening after 7 o'clock in the lobby of this building, there will be a workshop in which you'll be able to make your own astrolabe and use it for observations later on this evening. There's an example of a celestial globe, which is a spherical depiction of the heavens, and an armillary sphere, this one in Ibn Battuta Mall in Dubai. And you can see there's one man on the plumb line, there's another scribe, and then there are two men up the top turning the rings to facilitate the observations. A drawing of the giant quadrant at the Moraga Observatory. And a few words on the development of mathematics. At the beginning of the Golden Age, there were several systems of numerals available. The Babylonian base 60 system and the Roman numeral system, but both of them were very clumsy, especially when doing multiplication and division. And that resulted in the introduction of the so-called Hindu-Arabic numerals 1 to 9, which were much easier to work with. Some people have commented that the contribution of Muslim scholars to mathematics was zero. but in fact that was a very significant contribution. The Indian mathematicians did use a point as a spacer in their mathematical calculations and formulae, but they did not use it to create orders of magnitude. And the introduction of zero made orders of magnitude possible, as well as very large and very small numbers, and made modern arithmetic, as we know today, possible. They also invented fractions, and through the use of the zero, decimal places. And major advances were made in plane and spherical geometry, plane and analytical algebra, which was invented by Khwarizmi and others, and plane and spherical trigonometry. And there we can see a 13th century Arabic rendition of Euclid's proof of the Pythagorean theorem. I'll just comment on Euclid's Elements. It was translated by several scholars into Arabic, and the lower one there, Al-Husayn ibn Musa ibn Shakir, is one of the three Banu Musa brothers. And remarkably, he translated the first 6 books of Elements and then decided to just solve the rest of the propositions himself without bothering to read Euclid's solutions. And of course, we come across these numeral systems in everyday life. There's a clock with the hours shown in Roman numerals, the minutes shown in Arabic numerals, and if it's run on a computer chip, it will also have the 1 and 0 computer code. Deal with cartography, navigation, exploration. I'll mention 2 famous cartographers. Al-Idrisi, he worked from Palermo in Sicily in the court of King Roger II and created several famous world maps. Piri Reis was an Ottoman navigator and admiral, spent most of his life at sea and created extremely accurate charts of the Mediterranean Sea. So there we see one of Al-Idrisi's early maps, and remember that on their maps, like the Chinese, south is at top and north is below. So if you invert this map, you'll see there a likeness of the Iberian Peninsula and the Mediterranean Sea. This is a compilation of 70 of the maps produced by Al-Idrisi. And here we can see Europe quite clearly, with Spain and Portugal over there, France, Italy, and then the Arabian Sea. So these were by far the most accurate maps available at the time. And this artist's impression shows Al-Idrisi demonstrating his new map and globe to Roger II. Here's one of Piri Reis's maps produced in 1513, and it was only the second map ever produced that showed the east coast of South America, and it shows it with much more accuracy than the first map. But it's the first ever map to show parts of Antarctica down here. And this map became famous because it was lost and then refound in 1929 in the Topkapi, Paris. Some of the great travelers I can mention: Ibn Battuta, who went on the Hajj and continued traveling for 29 years, traveling over 120,000 kilometers, walking, riding donkeys and camels, and in simple boats, visiting over 44 modern countries in 29 years. Very fortunately for us, he was persuaded to write the diary or Rihle of his travels, and it's one of the most lucid accounts of society in the Middle Ages. A totally different man, Zheng He, he was the Muslim admiral of the Chinese fleet, and over a period of 28 years embarked on 7 great voyages to over 30 countries, traveling in the Indian Ocean and almost certainly also in the Atlantic Ocean. So there we have Ibn Battuta, and here we have Zheng He. And Zheng He's treasure ships were the largest ships known until the First World War. And remember, we're dealing with the 15th century here. Absolutely enormous ships, and compared there with the little Nina in which Columbus discovered the New World. The treasure ships were so big that they carried live animals on board. They had enough space to grow crops. They had special ships for carrying fresh water. And it is strongly suspected that in the purple shows Zheng He's definite voyages. It's strongly suspected that Zheng He did round the Cape go up the east coasts of South and North America, around the north of Greenland, which was possible at that time, and then back down the west coast of Africa. But that is still controversial. Of course, travel on land was also very important for trade and on pilgrimages, and this greatly extended the reach of the Islamic Empire and of the findings of their scientists. Muslim scientists were also the first to use a directional compass with a magnetic needle on a consistent basis. The Chinese had used magnetic needles before, but it was mainly for fortune telling and other purposes. Chemistry. And here we have a great scientist in Jabir ibn Hayyan, who lived from 721 to 815. And he's regarded as the father of quantitative chemistry. He pioneered many of the techniques that are commonly used today, like distillation, crystallization, sublimation, oxidation, filtration. He was the first to distill many of the major acids, as well as antimony, arsenic, mercury, and other chemical elements. And he applied his knowledge in useful ways as well. He made waterproof fabrics, fireproof paper, inks that could be read in the dark, varnishes, paints, glazes, and a whole variety of other practical applications. He had a rather odd attitude towards communication. He felt that anyone who didn't have the same level of expertise as he had should be excluded from understanding what he found. So he wrote his work in a very garbled sort of an esoteric code. So unless you were fully familiar with these techniques, you literally couldn't understand it. And in fact, this is where the word gibberish comes from the name Jabir ibn Hayyan, who was known in the West as Geber. But he also had very good practical advice, in that he advised people to use the experimental method and observation to test their ideas. Because, of course, he and other early scientists had inherited from the Greeks that the way they proved their ideas was through logic and reason and discussion, rather than through experimentation. So Jabir ibn Hayyan was one of the first people to emphasize the importance of experimentation. And here we see some early chemists, and this was really at the changeover from alchemy to chemistry, way back in the 9th century. And you might recall from the history of European science that even Isaac Newton was still dabbling in alchemistry many centuries later. And here, another great chemist and medical scientist, Al-Razi, he also worked at that transition from alchemy to chemistry. And many practical applications were made, for instance, dye making and also paper making. Now, this is an interesting object. The general opinion in the West is that the battery was invented by the Italian Alexander Volta. And here is shown demonstrating it to Napoleon in 1799. But in fact, something called the Baghdad battery was found underground in Baghdad in about 250 in the Common Era. It consisted of a clay bowl with a metal and a copper electrodes, and it had a light acidic liquid inside, as determined by the residue left behind. When I was at the Bahrain Science Center, we made one of these, and it worked. We were able to produce enough electricity to light up a little LED light. So it seems the battery was invented over a millennium earlier than we thought. Now, in the environmental scientists, I'll mention one, my favorite, Al-Jahiz. He lived in the 8th and 9th century. He contributed to botany, geography, geology, and zoology, and was quite an extraordinary man. He wrote over 200 books. He was a literary giant of his time. And one of his most famous books is a 7-volume Book of Animals, in which he documented all known animal species through proverbs, poetic descriptions, and discussions. But perhaps his most important contribution is he was one of the first ecologists. He discussed pollination, predator-prey relationships, symbiosis, animal communication, the structure of ant colonies, breeding strategies, He also recognized that fossils were the remains of animals that had died, and that simple forms had probably developed into more complex forms. And in a recent history of the theory of natural selection, he is the one Islamic scholar who's mentioned. And here is a replica of his famous book of animals that we created. Of course, there were also many botanists, because knowledge of plants was very important for producing herbs and dyes and other products. Now, flight would seem to be an odd one to include, but I noticed that a paper aeroplane is a theme of this year's WEP. But in fact, there were some pioneer aviators. This is how their contributions are dismissed in the official history of aviation, published by the Smithsonian on the centenary of the Wright brothers' flights. Attempt by suicidal tower jumpers to simulate the flight of birds. But another polymath, Abbas bin Firnas, should be mentioned here. He was a poet, astronomer, musician, engineer, chemist, and pioneer aviator. He developed, made, and flew a glider near Toledo in Spain in the year 875. And here is an account by a Moroccan historian, admittedly sometime later, based on contemporary accounts that were lost. Among other very curious experiments which he made, one is he's trying to fly. And basically, he says he covered himself with feathers, he flung himself from a hill into the air, and managed to glide for some time. However, he hadn't made provision for slowing down on landing, and he noted that birds bring their tail feathers in to slow themselves down. Ibn Battuta didn't have that, so he had a crash landing and damaged his back. He also made many other contributions. He devised a water clock, built the first indoor planetarium, made corrective lenses or reading stones, modeled the solar system using a chain of rings, and developed a process for cutting rock crystals. And in recognition of his work, there's a crater on the moon named after him, and also the airport in Baghdad. There were two other early aviators. Azafin Ahmed Salebi jumped off the Galata Tower in Istanbul and apparently glided across the Bosphorus. And his cousin, Lagari Hassan Salebi, is reputed to have done a rocket flight in 1633. By the way, both of them came to rather sticky endings. Azafin was regarded to have supernatural powers, and he was unfortunately executed. And Lagari Hassan, as a reward, was given some gold ingots and then sent to the army, where he was killed a few weeks later. Now, we're not absolutely sure about the authenticity of these two claims. The only existing record is written by a relative of theirs some years later, but they're certainly worth investigating. All of those early aviators studied the flight of birds, and this is one of the experiments that the Salabis did. They created this flat metal thing, and if you moved along it, your arms created the flapping motion of a bird's wing, because they realized that birds don't flap their wings up and down. It's actually a motion like that. Deal briefly with hydrology and town planning. Many of the cities and villages were in arid areas, so water provision was critically important. And these are examples of the water channels which are controlled by the water bailiffs at Al Ain in Dubai and throughout the arid countries. And as an example of the magnificent water reservoirs that were built, this one at Al Qarawwan in Tunisia, built in the 9th century, is still fully functional. And in terms of town planning, here's a description of Baghdad in the 9th century by the historian Amin Malouf. It has 1,000 physicians, an enormous free hospital, regular postal services, several banks, branches as far afield as China, excellent water supply system, comprehensive sewerage system, and a paper mill. What he doesn't mention is they also had checks, street lamps run on kerosene, irrigated fields, fortifications, and fountains. So extraordinarily well developed compared with European cities and villages at the time. And there's a plan of 16th century Diyarbakir in eastern Turkey, the mosque in the center, the narrow streets to create shaded walkways, fortifications all around it, and courtyards within the houses. Magnificent contributions were made in the fields of innovation, engineering, and robotics. And I'll mention just two groups, the Banu Musa brothers from the House of Wisdom and Al-Jazari, who mainly worked in the 12th century. The Banu Musa brothers were mathematicians and engineers. And one of the things they did is they created what they called trick devices, and they wrote a whole book about them. And these are devices that are very similar to the interactive displays that we have in modern science museums and science centers, where you engage with it to learn about the principles, in this case, of hydraulics. Many mechanical firsts were achieved by these engineers, automata or robots, cams and camshafts, cranks and cranshafts, rocker arms, pistons, cylinders, siphons, and so on. Now, individual elements of these had been used by previous societies, but none of them had put them together into complex machines. Al-Jazari worked for the king of Diyarbakir from 1180 to 1206 and made many utilitarian devices for him, including water pumps. But he also made robotic machines, some of them quite whimsical, as well as magnificent water clocks. This is a reproduction of his book that we created. He also created combination lock boxes. The king asked him to develop a portable timekeeping device, because all timekeeping devices were large and fixed at the time. So Al-Jazari invented the scribe clock, which has a water reservoir and a float and a mechanism which causes the scribe to move around and tell the time. Like the Banu Musa brothers, he also created playful machines. This is his diagram for the centrifugal flute, and here's the one that we made for our traveling exhibition. As long as you continue to top up water in that reservoir there, this rocker arm dispenses the water right and left, creates partial pressure differences, and the partial vacuum causes a high-pitched flute sound. Al-Jazari also made this robotic man, because the king said, I would like to perform my ablutions, wash my hands before prayer or eating in private. So he created this robotic man, which was placed in front of the king, poured water into a basin. The king then washed his hands, and then the left arm came forward and gave the king a towel and a comb, and then afterwards the robot retreated. And this is a wudu machine to provide the public with water for washing their hands. And one of many examples of Al-Jazari's water-raising machines. This is the one scoop, and it was the very first complex machine to use a crank, a device that converts rotary action into linear action. And probably his most extravagant and famous invention was the elephant water clock. That's his original drawing. And the reason why we've been able to make it is because towards the end of his career, the king of Diyarbakir said to Al-Jazari, I want you to record all your knowledge. So in great detail, he described his 50 greatest inventions and did detailed drawings of components of them and the whole thing. Those were translated into English, and we've been able to build from Al-Jazari's original descriptions. So there's a small version, a 2-meter tall version of the elephant water clock that we made, and that's the 11-meter version on display in the Ibn Battuta Mall. Now, what's significant about this sculpture, this water clock, is it celebrates the universality of Islam. It's got an Indian elephant, Persian carpets, an Egyptian phoenix, a Chinese serpent. It's got people wearing clothes from the Middle East. It uses the Indian water perforated basin technique for driving its mechanism. And basically what happens is that a series of balls loaded up at the top there fall into the falcon's mouth, then into the serpent's mouth. The serpent rotates downwards. The balls fall into this vase, which causes mahut to drum on the elephant's neck. And that then causes the perforated basin to sink inside a water reservoir here. And when it hits the bottom, the scribe moves his hand to show the time. Al-Jazari also designed and built a castle clock in which musicians play as a result of the movements of levers driven by hydraulic pressure. And there's the musical boat, which paddled around on little lakes in the king's palace. and the force of the water caused the musicians to play their musical instrument. Al-Jazari has been recognized worldwide, and I notice there's a building here as Kaus as well recognizing him, and I think it's well due. Now, I'd just like to mention that somewhat later, Taqi al-Din continued Al-Jazari's work, produced, for instance, this water-raising machine using pistons and cylinders. So to summarize some of those inventions, not by any means all of them, here some are listed. I've mentioned a few of them, others are new. But they really have impacted on the everyday life of people right through to today. Reciprocal cams, reciprocating pumps, scalpels, and many other medical instruments, scissors, segmental gears, etc. This era of innovation also saw the first industrial uses of wind, tidal, water, and steam power. So windmills from the 7th century, tide mills, water mills, and even steam mills in the time of Taqi al-Din. He wrote a book called The Sublime Methods of Spiritual Machines, including a steam turbine to rotate a meat on a stick. And a colleague of mine and I in Cape Town are busy making one of those ourselves. The first factories were also created at this time, factories to make ceramics, glassware, chemicals, clocks, carpets, pulp and paper, perfumery, oil products, etc. Let's move on to medicine and pharmacology. Here are two giants in the field, Ibn Sina, who is a great surgeon, medical man, also very conversant on plants, and Al-Zarawi, who developed many novel surgical instruments. And just a short list of some of their contributions to medicine. Hospitals in which people received free care, but they were also teaching hospitals associated with universities. They had mobile hospitals, had treatments for almost all known diseases, and thousands of medicinal drugs, the first dispensaries and pharmacies, surgical instruments, specialist physicians and surgeons. They introduced catgut for surgical stitching, musical theory, and had separate places for the mentally ill. And there's an example of a Maristan Mosque hospital in Cairo. They really were magnificent structures. Here's an early dentist at work. Of course, they invented the syringe. And they're examples of some of Al-Zarawi's surgical instruments. Another interesting finding is that Ibn an-Nafis, who is a medical specialist in 1210, he was the first to find the double circulation of the blood. In other words, from the heart to the lungs, back to the heart, and then to the body. Although in most medical texts, this is credited to William Harvey some 500 years later. Move on to physics and optics. I mentioned two specialists in physics, Ibn Sina and Al-Kazini, and you can see the various fields in which they were able to make contributions, centuries ahead of their time. But I'd like to concentrate on Ibn al-Haytham. He made contributions on the functioning of the human eye. He created glass lenses, was the first to split white light into color long before Newton, studied the effects of parabolic mirrors and lenses, created the pinhole camera, which led to the camera obscura and the camera, and also studied linear perspective, and is also given credit for developing the scientific method. Al-Jazari started his career in Turkey, but he was initially an hydraulics engineer who was attracted to Egypt, where the ruler wanted someone to solve the problem of the Nile flooding. In other words, tame the Nile River. And Al-Jazari foolishly agreed to try to do that. But he realized soon that even his engineering expertise and prowess couldn't tame the Nile. And he also knew that the ruler was a very ruthless man. If you failed him, you got executed. So he solved that problem by pretending to be insane, because he knew it was illegal to execute insane people. And he was put under house arrest, and it was during this time that he did his famous experiments on the properties of light and how vision works. One of the things he did is he got the eye from a dead ox, and he dissected away the tissue at the back so that he could see the image that was being projected onto the retina. And he noticed the image was upside down. He also created a camera obscura, which is basically a dark room with a small hole. The light comes from the outside, and the light ray from the top of the minaret went through the hole and to the bottom of the screen. And the light ray from the bottom of the minaret went through the hole to the top. And once again, that was proof that light travels in straight lines, and explained why the image is upside down on the retina of the human eye. And the camera obscura, of course, went on to be something that entertained people in many countries over the world and led to the modern camera. And here in a light laboratory in Bahrain, we recreated Ibn al-Haytham's laboratory. We redid some of his experiments, but we had the benefit of electricity and to show that light travels in straight lines. So Ibn al-Haytham really was a major disruptor, as we use the term today. He inherited a theory from the Greeks that our eyes see because rays emanate from our eyes and bounce off an object and then come back. And he was able to show, not just by reason and logic, but by observation and experiment, that in fact light reflected from the sun off objects comes into our eyes, and that's how vision works. As far as the scientific method is concerned, Hero of Alexandria is usually credited with the first one to discuss it, and then various other European scientists, especially Roger Bacon. But Jabir ibn Hayyan and then Ibn al-Haytham were really the first one to create the hypothetico-deductive method that we use today. Briefly mentioned sociology and economics, and the giant there was Ibn Khaldun. He worked in a number of different fields, but most importantly, he wrote about how nations rise and fall, and he predicted the fall of the Ottoman Empire and gave various reasons for it. He wrote this great book, Muqaddimah, basically an introduction to the history of the world, and his own life was full of tragedy and full of incident. He lost his parents in a shipwreck. So, you know, he wrote from experience. There are many other ways in which those early scholars have influenced our lives today. These are examples of the many hundreds of words in English that are derived from Arabic. And they're not only in the fields of science and technology, but also in many other fields. Now, I'd like to end by discussing why did science flourish during that golden age of Islam. And there are many reasons, and I think primarily among them is the Islamic faith, which, as you know, is far more than a religion. It's a whole way of life. So the way in which that faith encourages people to go about their lives definitely encouraged creativity and productivity among scientists. Building on the ancients, they were aware of the work of the ancients, but they built on it, they improved on it, and they had the attitude that just because they are authorities, they're not necessarily right. And in many cases, as in the case of Ibn al-Haytham, they proved that they were wrong. And at times in the 9th and 10th centuries, in the Great House of Wisdom in Baghdad, which was started by Ibn Rashid in about 786, and then continued by his son Khalifa al-Mamun in the 10th century. In the 9th century, these were great places of learning where people of all cultures came together. They had huge libraries. There was intensive discussion. So that promoted the building on the ancients. And there we can see a Turkish manuscript depicting Aristotle teaching Islamic scientists. Another reason is the introduction of modern arithmetic and the Arabic numerals and the introduction of zero. Use of trigonometry to predict lengths and measures and angles, which greatly facilitated developments in astronomy, surveying and navigation. The Houses of Wisdom were precursors of modern universities. They encouraged people of all cultures to come together and share their thoughts. Even children were encouraged to come and listen at the feet of the great masters. There's a drawing of a House of Wisdom in Baghdad. Some of their libraries had over 100,000 books, and these books, of course, were in various languages. The teaching hospitals greatly facilitated teaching and learning in medicine, but also in plant sciences and pharmaceuticals. The great astronomical observatories that were developed improved our knowledge of astronomy, but also of navigation. The paper making and production of books. Great battle in Samarkand in 760 or 50. The paper making techniques of the Chinese were discovered. But great advances were made on them because the Chinese mainly made paper out of silk, which wasn't readily available further west. So the Islamic scientists were able to make paper out of wood pulp, out of rags, and a whole variety of other materials. And for instance, by 1180 in Fez, there were over 400 paper-making workshops in that city alone. And there you can see the process of early paper making from wood pulp. Ethic of sharing knowledge. This was very much a part of the Islamic way of life and wasn't shared in England, where the top scientists spoke and wrote in Latin, and they didn't share their knowledge with the general population. Encyclopedism was another trait. There were, of course, some great encyclopedias from the ancients, and I'll list a few of them there. But if we look at just some of the encyclopedias written by these Islamic scholars, it was part of their whole work ethic that before they died, they recorded their knowledge. And some of them literally wrote hundreds of books. And many of them did them on a collaborative basis. And because they were polymaths, they were able to write in a variety of fields, but also integrate knowledge in those fields. Patronage of science was extremely important, and it's evidenced by this great university as well. There was great support for science and technology. The ethos of innovation, as shown by Al-Jazari, the Banu Musa brothers, and many others. Respect for scholars, and two quotes here: "A man's deed elevates him above others, not wealth or power." And in the Quran, God will raise up in rank those of you who have been given knowledge. So scholars were highly ranked within society, which once again differs from Western Europe at that time. The support of religious leaders, and I'll list just some of them there. Some of them, their pride and joy was the level of scholarship in their caliphate, and many of them were prominent scholars themselves who took part in the debates, the experiments, and the observations of their scientists. The tolerance and academic freedom. And Al-Kindi emphasizes we ought not to be embarrassed of appreciating the truth and obtaining it wherever it comes from, even if it comes from races distant and nations different from us. So there was very much a sort of universal view of science and scientific collaboration. The development of the scientific method by Jabir ibn Hayyan and Ibn al-Haytham, Al-Kindi, and others. The extent of the Islamic Empire. Of course, it extended at its greatest dimension right to the west, to Spain and Portugal, southwards in West Africa to Timbuktu, across North Africa, the Middle East, the steppes, down East Africa to Zanzibar, and then into Southeast Asia. It really was an enormous area. Extensive travel within this enormous area, on trade, on pilgrimages, and in other ways. And the universality of the Arab language. It was, at the time, the language of science. Let's also not forget the contributions of women scientists. And I can mention two here. Fatima Al-Fahiri, who was an art and building patron. She founded the Al-Kuala Rowan University, which is the oldest continuously operating university in the world, in Fez, Morocco. And Ijulia Astrolabi in Aleppo in Syria, who is a famous designer and maker of astrolabes. But the journey is not over. I believe we're now entering the second golden age of Islamic science. This is epitomized, for instance, by the Nobel Prizes to Abdus Salam, who worked in Pakistan on theoretical physics, awarded the prize in 1979, and Ahmed Zewail from Egypt, who worked mainly in the USA, on femtochemistry, awarded in 1999. Femtochemistry is a recording of chemical reactions at a very fast rate, in fact, in femtoseconds, much more accurately than ever done before. But the second golden age of Islamic science is also epitomized by the development of facilities, such as the new Bibliotheca Alexandrina in Alexandria in Egypt, new universities such as this, new science centers and museums, strong government support and patronage, active translation and research, and the recruitment of top scientists and educators. So CAST, I think, is a classic example of this new approach to universal development of science. Our museum, MOSTI, here at CAST, is an example of how we're trying to raise awareness among the general public of the importance of science and technology. And the Science Oasis in Riyadh and the Science Center networks and science festivals that are being developed in Bahrain, in Abu Dhabi, the new Science Museum in Dubai, all of those epitomize the new approach to placing science very central in our society's development. I'd like to end with this famous Muslim quote, "Seek knowledge from the cradle to the grave." I think this really epitomizes the work ethic of those great Islamic scholars. Thank you very much.
Thank you, Mike. That was an impressive demonstration of contributions across far more fields than I had known about. Thank you, Mike. That was really wonderful. Okay, so let's take some questions from the floor, please. And I think we have a roving microphone. Is that a question that didn't happen? Sir, we have one here, yep.
Thank you for an excellent lecture. I have a question. So what happened then, after, let's say, the 14th century? And why did the science decline? And did it have anything to do with the Ottoman Empire? I'm just trying to find sort of generic reasons.
Thank you. Could I have my slides back on, please? And I need to go to my last slide. I anticipated that question, so I have 2 slides to answer it. Okay, let's quickly whip through to the end. How did it end? The first crippling blow was the Mongol attacks on Baghdad in 1258. 2 million people killed, libraries, hospitals, schools, observatories, and houses of wisdom ransacked, burnt, or the contents stolen. And as a contemporary observer said, the Tigris ran red with the blood of the scholars and black with the ink of their books. Also, the loss of Spain, with Granada holding out until 1498, and the gradual reduction in the extent of Islamic influence, the increasing sophistication of Western scientists and their increased mobility, erosion of values around the fringes of the Islamic world, also the greater mobility of Western scholars, who started on their voyages of exploration in the late 1400s and 1500s, brought back a lot of new information. And of course, they were building on the libraries and the translated works of the Islamic scholars. So, a whole lot of things, socio-political things, contributed to that decline.
Events that made the truncation of the era so fixed, or were there other reasons why the knowledge didn't get translated and become a greater foundation to the Renaissance, say, in Europe?
Yes, there were these two phases of translation. In Baghdad and elsewhere, a massive effort was put into translating early Greek, Sanskrit, and other manuscripts into Arabic. And then much later in Toledo in Spain, there was a translation center translating the Arabic into Latin and then later into English. Now, the extent to which that translated information was used by scientists in the West differed from discipline to discipline. In some areas, like technology and engineering, the work of Al-Jazari remained well known and was built on. In other words, such as medicine, a lot of it was ignored, and only in fairly recent times have the contributions of, for instance, Ibn al-Nafis and others been recognized and acknowledged. So it differed from discipline to discipline. But a lot of the work was available in either Latin or English. And of course, Latin was a language that many of the early European scholars worked in. So I think you're probably right that the translation process in that second phase wasn't as efficient as it was in the first phase. And also the whole ethic of accepting knowledge from other societies. There wasn't an arrogance in the Islamic world. They accepted knowledge from other societies, whereas there was a certain amount of arrogance from Western Europe that they didn't need to build on anything. They were capable of creating it anew. But even scientists such as Copernicus and Galileo and Newton acknowledged the work of Islamic scientists and mention it in their writings. I haven't mentioned another character, and perhaps if there's a moment I can say something about him. His name was Zerhab, and he was known as the Blackbird because he had a harmonious voice and a dark skin. He had nothing to do with science, but he had a massive impact on the culture of people in Europe. He was a fashion designer, believe it or not, and he was a musician and a singer and someone who dealt in etiquette and ethics. And when he was attracted to Spain, some of the things he introduced were the tablecloth, the napkin, the fork, three-course meals, different clothing styles for different seasons of the year, a colorful drapery for curtains and cushion covers and sofas. So he actually revolutionized the social life of people, initially in the Islamic world living in Andalusia, and then later Europeans. He also introduced poetry readings and really had quite a massive impact on the social lives of people.